And so what we're going to be doing is we're going to be looking at this in more detail as far as the heat goes. Excuse me. If you heat a solid, it might not melt. It depends. Like, for example, if you heat a piece of aluminum, is it going to melt right away into a liquid? No, what's going to happen is it's going to get hotter and hotter, and eventually it's going to hit a temperature at which it begins to melt. That temperature is called its melting point. And so when we're dealing with heat, there are two ways that heat is absorbed by what we're looking at, called the system. One way is we can heat or cool an object. And so it's a solid piece of aluminum, it's going to get hot, or if we cool it, it's going to get cold. When we heat or cool an object, then the heat, which is given by the symbol little q or big Q, this is equal to the heat, is equal to the amount times something called the heat capacity, or specific heat. We'll just say specific heat, or heat capacity, times delta T, the change in temperature. Now let's just say change in temperature. All right, so normally when we're thinking about heating and cooling an object, we use this equation. Q is equal to mc delta T. So for example, if we have some water, let's say I have 25.0 grams of H2O liquid at 25 degrees C. If I heat the water, is it going to start to boil immediately? No. What's going to happen is it's going to get hot. And so I can heat it up until, actually I can't heat it up to any temperature. Let's say I tried to get hot water at 200 degrees C. Am I going to be successful? No, because what's going to happen before 200 degrees C is it will start to boil. And do you know at what temperature water starts to boil at? What temperature? 100 degrees Celsius. That's called its normal boiling point, right? Normal boiling point means what? It's the boiling point when we're at normal pressure. What is normal pressure? 1 atmosphere. Now, if we're at other pressures, then it's either going to boil at a higher temperature or at a lower temperature, depending on what the other pressures are. So let's take a look. The hottest we can get the water is 100 degrees C. And so what we need to do is we need to find out how much heat we have to add to this. So if I have 25 grams of water at 25 degrees C and I want to make it 25 grams of water at 100 degrees C, how much heat does that take? Well, the heat is going to equal the amount. The amount is 25.0 grams times C. C is something we look up. For water, a lot of people know what it is. It's 4.18 joules per gram degree C. 4.18 joules per gram degree C. And so that's from a table. Times our delta T. Our delta T is T final minus T initial. So T final is 100 degrees Celsius. T initial is 0 degrees Celsius. Or not 0, sorry. T initial is 25 degrees Celsius. And so the temperature increased by 75 degrees C. And so let's calculate how much heat was required to do this. And so I have 25 times 4.18 times 75. And it's going to take us 7,837.5 joules, or 7.84 kilojoules. And so we're going to need 7.84 kilojoules worth of heat to warm up this water. Okay, once I warm up the water to 100 degrees C, what happens if I keep adding heat? Is the water going to get hotter? If I keep adding heat to this, will the water get hotter? The water is not going to get hotter. Water is not going to get hotter than 100 under normal pressure conditions. And so where does all that energy go? Yeah, that energy goes into vaporizing the liquid. And so that's the other way. We call this heat in phase change. And so energy in a phase change. So this is 2. So now all that heat, all that energy is going into vaporizing. It's going to go into boiling that water. And so here what's going to happen is I'm going to have 25.0 grams of H2O liquid at 100 degrees C. And then all that energy goes into vaporizing it into a gas. So I'm going to have 100 grams of steam. Sorry, not 100 grams. 25.0 grams of H2O gas, steam. Now, interestingly, the steam is going to also be at 100 degrees C. And so the temperature didn't change. All that energy went into breaking the intermolecular forces, the hydrogen bonding interactions, and the dispersion forces that hold the water molecules together. And so I'll completely vaporize it. Now, how much energy is required for that? Well, it's a different equation. So the other equation is when we have a phase change, that is, we're going from the liquid phase to the gaseous phase or some other transition, then Q, the heat, is equal to the amount times the heat of vaporization. For this case, or just the heat of the phase change. In other words, it's going to be the amount times delta H of the phase change. And the phase change could be vaporization, which is boiling, or it could be condensation, which is the reverse, or fusion, we call it melting, fusion, or freezing. Those are the common phase changes. So in this case, we are boiling the water here. And when we boil the water, how much heat does that take? So I know the number, it's just, but not in the units that we need. I know it's 44 kilojoules per mole of water, but we want it per gram, so I can convert that. But what I'm going to do is I'm just going to use our tables. Get it here. So when I look at the heat of vaporization, I go here. Here's water. Water boils at 100 degrees C, and its heat of vaporization is 2.26 kilojoules per gram. This is what we call heat of fusion or melting. So water melts, ice melts at 0 degrees C, and it's going to cost you 333 joules per gram to melt the ice. Well, we're going to boil the water. Boiling is going to take more energy because we have to completely break the intermolecular forces. When we melt it, we don't have to completely break the intermolecular forces. They're still present holding the water molecules together, but it's not as optimized, not as strong. And so this is the number here, 2.26. And so Q is equal to the amount. We have 25.0 grams of water that we need to boil. And then that's going to be times 2.26 kilojoules per gram. And so the grams cancel out, and that just gives us kilojoules. So how much energy does it take to vaporize that water. And so 25 times 2.26, we get 56.5 kilojoules. So we compare this, you know, to warm up the water costs us, what, around 8 plus kilojoules. To boil it costs quite a bit more, 56, 57 kilojoules. So those are two examples. And one example of heating and cooling an object, we just heated it. Cooling would just be the reverse. And the other is the phase change. Now, these aren't all the phase changes. Heat of fusion is melting. Heat of vaporization is boiling. But what we can also do is we can take steam and condense it back to a liquid. That's a reverse of vaporization. Well, if we reverse the process, then it's the opposite. And that is, rather than absorbing 2.26 kilojoules per gram, it would release. We need to remove 2.26 kilojoules per gram. And so it's negative. And so the heat of condensation is minus 2.26 kilojoules per gram. And if we melt it, it's going to cost us 333 joules per gram. If we freeze it, we have to remove that. And so we'll have to remove 333 joules worth of energy for every gram of water that we want to freeze. And so let's take a look at some numbers here first. So we look at the heats of vaporization. You know, what has the highest heat of vaporization that you see here? Looks like aluminum. So it's going to cost a lot of energy to boil aluminum, which is 10.9 kilojoules. Then it looks like iron, copper, some of these others. These are others that are pretty high. But water is actually kind of high too. So 2.26, even though it might look small, isn't so small. And then we look at melting. As far as melting goes, which is the highest, which is the lowest? Yeah, it looks like sodium chloride is the hardest to melt, 519. Sodium chloride requires a lot of energy, 519 joules per gram. And take a look at its melting point. Its melting point is at 801 degrees C. Has to be awfully hot. What else do we see? The lowest would be like mercury. Here. Mercury has a very low heat of vaporization as well, 0.3. And so we see a range of values here. We don't memorize any of these. You can look them up. These are the specific heats here. Can you see which is the highest specific heat, which is the lowest specific heat that you see on this chart? See, I see the highest is water. Water has a high specific heat. Do you know what that means? Well, look at the units here. The units are going to be joules per gram degrees C. And so the way you read a joule per gram to degree C is like this. Water, liquid water takes 4.18 joules of energy to heat 1 gram of water by 1 degree C. So it takes a lot of energy to warm up. Okay, what's the lowest that you see? Gold? Lead. Lead here. If we look at lead, lead only takes 0.13 joules of energy to heat up 1 gram of lead by 1 degree C. So it's very easy to heat up lead. Its temperature is going to rapidly increase, whereas water, it's going to take a long time to heat that up because it's got to absorb a lot of energy before it starts increasing its temperature. And so things with a high specific heat take a lot of energy to warm up. Things with a low specific heat take a little bit of energy to warm up. Oops. So whether it warms up or cools down or melts or vaporizes depends on where it is in the temperature range. So if it's below the melting point, then we add heat or remove heat, it's going to warm up or cool down. If we're at the melting point, then we're going to melt or freeze. If we're between the melting point and the boiling point, then we got a liquid, it's either going to warm up or cool down. And if we're above the boiling point, then it's going to be a gas. That can also warm up or cool down. And so we've got to see what phase we're in, that is, what state we're in. So somebody we reformatted this. So this says how much energy is needed to vaporize 188 grams of a liquid if its heat of vaporization is 1.13 kilojoules per gram. So how would we do that? Take a look here. Well, we're vaporizing. So if we're vaporizing, all the energy is not going into increasing the temperature or decreasing the temperature. All the energy is going into vaporizing. And so we don't even need the temperature. You know, we just need to know it's vaporizing. When it's vaporizing, the temperature doesn't change. So we're just going in and breaking the bonds. And so the equation that we need is Q is equal to the amount times delta H. In this case, the phase change is vaporization, so we need delta H of vaporization. Well, that's given here. It's 1.13 kilojoules per gram. And so it's the amount is 188 grams, 1.13 kilojoules per gram. Grams cancel out grams, and that leaves us with 212 kilojoules. And so just 212 kilojoules is required to vaporize that. How much energy is required to melt 25.0 grams of ice at 0 degrees C? Okay, so again, this is a phase change. We're melting. And so the equation is Q is equal to the amount times delta H. Now, what is the change? It's melting. It's also called fusion. So delta H of fusion is delta H of melting. We look up delta H of fusion in the book, and it's 333 joules per gram. This is from table 15.4. And so I'll plug it in. The amount, 25.0 grams. Delta H of fusion, 333 joules. That gives us 8,330 joules, or 8.33 kilojoules. Yeah.
What's Latin mean?
What does what mean?
Latin mean. Because I've heard of Latin mean fusion. Is that just the same thing?
Where did you see that?
Well, I've heard about it in a previous course.
Delta H of lat? Is that
Latin.
lattice?
No, Latin heat of fusion.
Latent?
Yeah.
Latent heat of fusion?
Sorry.
Latent heat of fusion is the same as delta H of fusion.
Okay.
It's not different, so it's the same thing. Latent. A lot of people don't bother with the latent, or they just call it heat of fusion, or just delta H of fusion. Latent is not necessary to have there, so it's optional. So this book doesn't use it. Okay. Now here, how much energy is required to change the temperature of 25.0 grams of water from 10 degrees C to 50 degrees C? So here we're just going to heat an object. We're going to heat it so the temperature climbs from 25 or 10 to 50. Sorry, 10 to 50. And so we're going to use this equation. Q is equal to the amount times C times delta T. The amount is 25. C, we look up in the book, for liquid water, it's 4.18 joules per gram degree C, which is fairly high. You know, this was the highest one on the chart, so water has a very high specific heat. Times delta T, which is 50 minus 10. T final minus T initial, that gives us 4.18 kilojoules. Now, we'll take a look at a problem here next, and then try to solve this. Okay, calculate the total heat transferred when 19.6 grams of ice, initially at minus 12 degrees C, is heated to steam at 115 degrees C. Okay, and so this is what's happening here, but I'm going to blow that up so we can see it a little bit more. This is called a heating curve or a cooling curve, depending on which direction we go. If we go from left to right, it's a heating curve. If we go right to left, it's a cooling curve. What's plotted on the x-axis is energy here. On the y-axis is temperature. So we start off with ice at minus 12, and we start to warm it up. If we're warming up ice, then what equation do we use? We use Q is equal to mc delta T. And so the solid warms. Can we heat ice all the way to 115 degrees C? Is that possible? No. We can heat ice up to a maximum temperature of, can we get ice cubes at 100 degrees C? No. In fact, the ice cubes are gonna, the max temp the ice cubes are gonna reach is gonna be 0 degrees C. Because at 0 degrees C, what's gonna happen is the ice is gonna start to melt. And so we're gonna take all that ice and warm it up to 0 degrees C. So we need Q is equal to mc delta T. All right, that's the first step. And we have to break this up into steps. So we're going to call this step 1. Q1 is equal to mc delta T. The amount of ice is 19.6 grams. Now we need the specific heat of solid ice. So I go to the table and look it up. Solid ice has a specific heat of 2.06. It's about half that of water here. Joules per gram degree C. So ice requires 2.06 joules of energy to heat 1 gram of ice by 1 degree C. And so the grams cancel out. Now I've got to cancel out the degree C. I'm going to cancel out the degree C by doing the delta T. And so what is my delta T? Well, the delta T is T final. The maximum temperature of ice is going to be 0 degrees C. Minus the initial temperature, which was minus 12 degrees C. So it's a minus, so the temperature increased by 12 degrees C. And so let's calculate how much heat is required to warm up the ice. And so that's going to be 19.6 times 2.06 times 12. 237. 237.312 joules. Okay, well, how many sig figs? I'm actually only allowed 2 sig figs, so I'll round it at the end. I'm not going to round it down. Okay, that's step 1. All right, once I heat up the ice to 0 degrees C, then I'm not going to get any hotter ice. If I add heat to it, where's all that energy going? It's not going into warming up the ice, it's going into melting the ice. And so in the next step, the temperature stays constant as I melt the ice. And so going from B to C here, the ice is melting until I've melted all the ice. There's no more solid ice left, and that's point C. And so how much heat is required to melt all that ice? Well, I'm going to call that step 2 over here. And so step 1 was to warm the ice. Step 2 is to melt the ice. And the ice is going to melt at 0 degrees C. And so we're warming the ice from minus 12 degrees C to 0 degrees C. Okay, when we melt the ice, Q is equal to the amount times delta H of fusion. Fusion is another word for melting. And so the amount of ice we have is 19.6 grams. And delta H of fusion, we'll look it up on the chart. Here. That's this column here. For water, it's 333 joules per gram at 0 degrees C. So 333 joules per gram. So the grams cancel, that leaves me with joules. So let's see how many joules of energy this requires. 19.6 times 333. And actually quite a lot, 6,526.8 joules. So this is what we have so far here. Okay, to warm the ice from here to here is going to cost us 237 joules. And then to melt the ice from here to here, to completely melt the ice, is going to cost 6,527 joules. 26.8 joules. Okay, so that's step one. Step two, step three. Step three is now all the ice is melted, and so we're left with liquid water. And so once we've melted all the ice, then step three is to warm the water. Now, the starting temperature of the water is going to be 0 degrees C. And so we're going to go from 0 degrees C. What's the maximum temperature I can get for water? 100 degrees C. So we're going to warm the water from 0 degrees C to 100 degrees C. And so that's warming an object. The object is a sample of water. So Q is equal to the amount times C times delta T, or MC delta T. And so the amount is 19.6 grams. C is 4.18 joules per gram degree C from the table. And T, delta T is T final, 100 degrees C minus 0 degrees C. So we're going to increase the temperature by 100 degrees C. And so this gives me 19.6 times 4.18 times 100. And so I get 8,192.8 joules. So it's going to take a lot of energy to warm that water up. Water has a pretty high heat capacity. So that's it. These aren't to scale. This should be 8,192.8 for that step. So step one, step two, step three. What's step four? Yeah, once I get all the water up to 100 degrees C and I try to add more energy, more heat to it, it's not going to get any hotter. What's going to happen is all that energy is going to go into boiling the water. And so step four is we're going to boil the water at 100 degrees C. And so I need the delta H of what? vaporization. And so I go back to the chart and look, delta H of vaporization is 2.26. And so Q is equal to the amount times delta H of vaporization. And so the amount is 19.6 grams. Delta H of vaporization is 2.26 kilojoules per gram. So 19.6 times 2.26, 44.296 kilojoules. This is 44.296 kilojoules, which is equal to 44,296 joules. So this step is going to take a lot of energy. To go from here to here, we're going to boil all the water. And that's going to take 44,296 joules. That takes a lot more energy than any of these, because what we got to do here is we got to completely separate all the water molecules. That is, completely break all the IMFs holding them together. And so this is going to cost us energy. But once we're at the end of this, we've boiled all the water. So 100% of the water has been boiled by the time we hit here. And we're just left with gas, gaseous water at 100 degrees C. And so the final step is we're going to warm up the steam. So this will be step 5. And that is just the heat, the steam. Steam is just, there's no phase change, it's just an object, gaseous water. And so Q is equal to mc delta T. M is 19.6 grams. C, we need the specific heat of steam. So if we look at the specific heat of steam, it's 2.00. This is very close to ice. 2.00 joules per gram degree C.